ladies and gentlemen, so the last talk for today will be by Alberto Cattaneo, who will speak about Poisson structures arising from corners of field theories.
Okay, thanks. So, well, this talk is based on work with several co-authors, and in particular with Giovanni Canepa on the part that I will only briefly mention and will not have time to discuss, but somehow the rest of the talking motivation for this part. Somehow the general idea is somehow to understand what happens on corners of field theory. So suppose that you have a field theory on some dimension here, just in 2 dimensions for simplicity, and suppose that the manifold has some boundaries here, for example, and suppose the boundary is also some corners, so in codimension 2. And the idea is that, well, if you didn't have boundaries, the field theory would just produce, say, a number, the partition function. If you have a boundary, you should expect the boundary to produce some Hilbert space and the bulk to produce a state in the Hilbert space. And, okay, what happens if you have a corner? Well, you should expect the corner to be quantized to some algebra, which acts on the Hilbert space it touches. And then when you want to glue corners together, basically you should just take the tensor product of the 2 Hilbert spaces over the common algebra. And at the classical level, on the other hand, you expect the boundary to produce some symplectic manifold and the corner to produce some Poisson manifold, and then you expect the symplectic manifold to a Poisson map to the common Poisson manifold, and the gluing is just a fiber product over the Poisson manifold, well, actually followed by reduction. Okay, so that's it. Now, okay, this is the picture we have in mind, and of course, this also can be reformulated in terms of shifted geometries, essentially what Tony explained, more or less. The bulk is related to some -1 shift symplectic structure. Whenever you go to the boundary and the corner and so on, you keep shifting higher, essentially. And then you reinterpret the shifted structure as symplectic Poisson and blah, blah, blah. Okay, just let me give you some, oh, why? Oh, okay. So let me give you some okay, some examples that comes from elsewhere, and later on we will reinterpret it as an example of the corner. So simply, this example is a finely algebras, which of course appears also in physics, and they are related of punctures, and say in the Basdomino-Witten model, or actually is also related to corners in Chern-Simons theory. Just let me give you just like the mathematical definition. So you start with some Lie algebra G, well, an example finely dimensional, with an invariant inner product. And then you look, first of all, to the infinite dimensional Lie algebra given just by maps from the circle to the Lie algebra itself, and you just define the D bracket pointwise. Okay, so this is just an infinite dimensional Lie algebra. And the interesting thing is that this infinite dimensional Lie algebra has a non-trivial cocycle, which is given here. So f and g here are Lie algebra value functions on the circle. You just take the differential of one of the two, and then you pair them in the Lie algebra. This gives you one form that you can integrate. And it turns out that this is a cocycle, and it's non-trivial. So then you can use this cocycle to define a central extension of your Lie algebra, as here. So namely, you define this new infinite dimensional Lie algebra G hat, which is this Lie algebra with pointwise bracket. Then you add a copy of R, central element. So an element here commutes with everything. And you deform the bracket here in such a way that in addition to the pointwise bracket, it spits off some constant element just by this formula. So explicitly, the bracket is defined here. So f and g are Lie algebra value functions, a and b are just constants, and the bracket is defined here. It has a term here, which is a pointwise bracket, and a term here, which is a cocycle. Okay, so so this a finely algebra is represented. What you're interested is its representation theory. This is related to the quantization I was mentioning when you want to quantize these corners. And well, the quantization in this case, well, is a representation theory of this finely algebra, which is essentially vertex operator algebra for this problem. As I said, it's related to Chern-Simons theory and Basdomino-Witten model. You might think of this actually as a Poisson algebra going to the dual. Usually you know that you have finite dimensional algebra. On the dual, you have a natural Poisson structure, I mean the Kirillov constant Suryo structure. Of course, in this case, you have to be careful because this is infinite dimensional. So by dual, I mean this thing here, which I call F related to the corner. Essentially, remember that we started with functions on the circle taking value in the Lie algebra, that is 0 forms on the circle tensor the Lie algebra. And we just dualize somehow using the locality. So basically, we dualize G as G dual, this is finite dimensional, but we dualize 0 form on the circle as 1 forms on the circle. Okay, so we regard this space and we think of it somehow as a Poisson manifold. It's an infinite dimensional Poisson manifold just by the Kirillov constant Suryo. By vector field. Of course, you have to be careful. This, well, by vector field is only formally defined. What you can do, however, is to associate a Poisson algebra structure on certain functions over this infinite dimensional space. So basically, okay, just one simple idea is instead of taking all possible functional, you just take only local functionals, and on local functionals, you have a Poisson algebra structure. So you think of this somehow as a Poisson manifold in this sense. Okay, you don't have a Poisson bracket of all possible functions, but on a nice class of functions you do. Okay. Now, here is another example, which we'll see later on is related to another field theory, actually BF theory in 4 dimension, but it's also related to gravity in 4 dimension. So the idea is the following. Now, again, we start with the finite dimensional Lie algebra G. At the moment, I don't even have to introduce an invariant inner product. And now we take a closed oriented surface, a 2-dimensional surface. Okay, so this I mean the 2-dimensional generalization. So the first step is again the same. We just take maps from gamma to G with a pointwise bracket. This is our infinite dimensional algebra. But now we have to introduce another ingredient, namely we pick 1 forms on the same surface gamma, tensor the dual of the algebra. Over here, we define the bracket to be 0. But the interesting thing is that we have a mixed bracket here. Basically, we just take, so these are 0 forms tensor the Lie algebra, so we just take the wedge product here, and then we just let the Lie algebra G act on G dual by the cojoint action. Okay, so it's somehow some pointwise extension of a cojoint action. And then we just we think of the direct sum as a Lie algebra with this bracket. So explicitly, you write it here. And now the interesting thing is that this infinite dimensional Lie algebra has a non-trivial cocycle, which doesn't require an invariant inner product. We'll say very simply here. So the first ingredient, you have F alpha. So F is a Lie algebra valued function, and alpha is a dual Lie algebra valued 1 form, and similarly here. And so what you can do, just let's explain the first term. What you do, you take the differential of the Lie algebra valued function on the second entry. So this will give you a Lie algebra value 1 form. Alpha is as a 1 form taking values in the dual of a Lie algebra, and you just can canonically pair them. So this round bracket here is just a canonical pairing between G and G dual. Okay, and so this gives you a 2 form on gamma, which you can integrate, and then you just simply skew symmetrize. And okay, you can verify that this is a cocycle, is non-trivial, so you can use it again to define the central extension. Okay, just the same trick as before. So here you have this pointwise Lie bracket, and here you spit out the central extension. And of course, you can generalize this. Well, I mentioned 2 generalization. One is instead of taking Lie algebra valued 0 forms or 1 form taking value in the dual, actually you can think of starting with a non-trivial G bundle over gamma. And then instead of taking the algebra values 0 form, you just take sections of this bundle, and for the dual, you take section of the dual. The only problem is how do you define the cocycle? Remember, there was this derivative. Well, you just pick an arbitrary background connection, and it's the covariant derivative. You can define these things. This is still a cocycle, so you can extend it this way.
Independent connection?
It does, yeah. It depends on the connection you choose, yeah. And another thing you can do is to deform the cocycle if you happen to have an invariant pairing, basically what you can do, well, basically you think of the pairing instead of being on the algebra on the dual, I mean, just, right? And basically you just pair together the two one forms that take value in the dual over the algebra, okay? And this gives you again a two form that you can integrate, okay? And this lambda is just some parameter. And this is also a co-cycle. So basically this way you get the whole family of the algebras. And this turns out to be related to four-dimensional BF theory. And this lambda is what is called the cosmological term, because it is related to the cosmological term in when you try to interpret BF theory as related to gravity. Okay, and in this case, as far as I know, that nobody has thought of studying the representation theory, which would be interesting already in the case of for the BF theory. But I will see in a moment. This is also interesting if you want to well, study corners in gravity. Now, I'm saying here this is just related to for DBF theory, is not exactly. I mean, the previous example was exactly Chern-Simon theory. This is only related to for DBF theory. Namely, to get for DBF theory, you have to do something more. So first of all, let's pass again to the dual of this Lie algebra, which, okay, I do it think locally, which we think now as a Poisson manifold, an infinite dimensional Poisson manifold, well, because Poisson bracket defined only for certain functionals. So let me call A and B the coordinates here. So A is just the algebra value of one form, and B is the two form valued in the dual. And then basically what you're interested in is a Poisson submanifold of this infinite dimensional manifold. So the Poisson submanifold is just defined by this equation. So f of A is well, you can think of this as a connection. F of A is its curvature, and you just say that the curvature plus this lambda times B is equal to 0 with lambda and lambda we had before. So if lambda is equal to 0, this just selects flat connections. Otherwise, it says that B is defined in terms of the curvature. And this is actually, this Poisson submanifold is a Poisson submanifold, I mean, a Poisson manifold associated with the corners of four-dimensional BF theory. Actually, if you really start from BF theory in the bulk, in the BV formalism, you end up on the corner with somehow a resolution of this Poisson submanifold. But you can equivalently just, or in this case, just present things this way. And now, how is four-dimensional gravity related to this? Well, first of all, well, four-dimensional gravity, well, the algebra it should be the special orthogonal group in 4 dimensions. Well, the physical version should be with the Lorentzian signature, but otherwise you can take the Euclidean version. But there is one further constraint that comes out from, well, the analysis of four-dimensional gravity says that, well, you have one additional constraint you have to impose here, not only these constraints, but in addition, you have to basically say that this two form that takes values in the dual of the algebra should be pure. And you can formulate this by saying that its Pfaffian is 0. So notice that in this case, well, you can identify this Lie algebra with 4x4 skew-symmetric matrices. And so you have the notion of a Pfaffian. Okay, so, I mean, I will not show you why this comes out, but essentially, this is the result. So basically, and then the other exercise you can do is you can check that when you impose these constraints, and well, you avoid the 0 value, which would be singular. Yes, yeah, you get a Poisson submanifold, and that's yeah. Okay, and so the idea that basically, well, the analog of I mean, the vertex operator algebra for gravity corresponds to somehow representation of the quantization of the Poisson manifold. So you start with this Poisson manifold, you go to this Poisson submanifold, then to this next Poisson submanifold. You should integrate this Poisson manifold to some associative algebra, and then you're looking for representations. Okay, actually, since we are talking about a dual over the algebra, well, you know what the quantization of this should be, and actually you know what the representation should be. Just look for representations of this Lie algebra, and then it turns out that, well, you can write down these equations in terms of Casimirs, and then basically this selects only certain representations. That's the point. So at the end, it's not so. If you know how to find the representation of what that infinite dimensional Lie algebra, the associated problem is just corresponds just to selecting certain representations. Okay, so just let me give you some very quick motivation of how these things appear. And the point is the following. So first of all, well, you know what I mean, the Poisson structure on a manifold M is, and as been mentioned already, this is also, well, you can define this by taking a bivector field that Poisson commute with itself, but you can rephrase this in the language of supermanifolds. So you just take the outcotangent bundle of your manifold, actually you shift it by 1, and then you reinterpret the Poisson bivector field as a function of degree 2 over here. And well, the canonical Poisson bracket on the cotangent bundle is, in this case, a Schouten noise bracket. So Poisson structure on M is the same as a function of degree 2 that satisfies this equation, well, which is similar to what we saw in Brian's talk, but now the next shift. If M is a graded manifold itself, then well, a function of degree 2 is not just a bivector field, it's a collection of a function of degree 2, a vector field of degree 1, a bivector field of degree 0, and so on. And well, the relation, this relation here just gives a lot of, well, relation between these components that have to somehow commute with each other in an appropriate way. But another way to express this is essentially that this defines an L-infinity algebra structure on the functions. So basically, the K-ary bracket is defined as follows. You take your K function, you pick your differentials, and then you just feed in the K vector field, and this will give you a new function. And this is just the K-ary bracket. And this the equation here corresponding to this equation tell you that this is an L-infinity structure, curved if pi 0 is different from 0. And well, this we would call a p-infinity structure because in addition, these brackets are multi-derivations. Okay. Now you can slightly generalize this. So first of all, instead of taking explicitly the shifted cotangent bundle, you just take a graded manifold with a symplectic structure of degree +1, and you just play this game. Since we are in the smooth category, it turns out that, of course, you can always identify this graded manifold with a shifted cotangent bundle, but in a non-canonical way. So, well, this is a choice you have to do if you want to go back to the previous discussion, and this is what we call choice of polarization. Now, let me just pick a very simple example, which appeared also in Brian's talk in, well, in a different version, but is essentially the same example. So start with a finite dimensional Lie algebra. You can take its dual as a Poisson manifold with the Kirilo-Constant-Suryo Poisson structure. This means that you have a function of degree 2 on the shifted cotangent bundle. But the point that you can view this shifted cotangent bundle, where this is a linear space, you can rewrite it this way, which means that, well, this is the same as a shifted cotangent bundle of G shifted by 1. Which means that now you can reinterpret this S as a function of degree 2 over here, which is now a collection given by a vector field, and so on over here. In principle, it turns out that the only component that is not 0 is a vector field of degree 1, and this turns out to be just the Chevalley-Allenberg differential. So you can interpret it this way. So here the point that the same data of a symplectic structure in degree 1 and this function of degree 2, the Poisson commute with itself, can be reinterpreted as the Kirilo-Constant-Suryo Poisson structure or the Chevalley-Allenberg differential. Okay, and there is a further generalization, which essentially is due to Ted Voronov. Basically, you forget the Poisson manifold, you just work algebraically. Namely, you just start with a graded Poisson algebra, an element of degree 2, the Poisson commute with itself. So in our example, this algebra was just function on the shifted cotangent bundle. And then you look for some splitting of this graded Poisson algebra into two summands, both of which should be Poisson subalgebras. You require H to be abelian, however. So in our previous example, these summand H were functions on the base, and G were multi-vector field of strictly positive degree. Okay, and then what you can do is now use well this function S to define an L-infinity structure on H. So what you do is the following: the K-ary bracket is as follows. So F1 and F2 of K are elements of this abelian factor abelians of man H. What you can do now, you can view them as element of A, and then you can start taking brackets, Poisson brackets starting with S. So first you take the bracket of S as 1, then iterate with F2 and so on. At the end, you get some element of A, but since you have this splitting, you can project down to H again. And it turns out that this is, so this is a projection, this turns out that this is, if you have this equation, this is again an infinity structure. Well, the advantage of this is algebraic procedure is precisely that, especially in the infinite dimensional case, we were not really working with all functions. We have just some nice Poisson algebra, for example, local functionals, so this works better. And the other reason that there are examples like gravity on the corners, where actually, if you want to stay at the nice differential geometry description, there would be a symplectic structure that gives the Poisson structure is actually degenerate. And you cannot go to the reduction, I mean, unless you give up smoothness. So it's better in that case. It's better to work in this setting. Anyway, if you have like a closed two form, you can associate with Poisson algebra. Anyway, also in the finite dimensional case, you just take those functions that happen to have a Hamiltonian vector field, and you can define Poisson structure. Okay, and then the idea is that, if you apply this to BV theories on some bulk, when you go to corners, you get such a structure. And maybe let me say very quickly, the simple example, which corresponds to the two cases I described, which is AKZ theory. I mean, I will not tell you what they are, so this is just last part. For those who know what AKZ theories are, if you have an AKZ theory, which means that you have some target here, some graded finite dimensional graded manifold Y, together with an exact symplectic structure of degree n-1, and the function of degree n that satisfies this equation, you can define a shifted structure on mapping spaces. So basically, you just take some K manifold, it's a shifted cotangent bundle, and then you consider the mapping space from this manifold to this manifold. And over here, you can induce a symplectic structure of degree n-1 minus K. Okay, so if you take K equal to n, you get the BV structure. These are why the method was devised. But if you take K equal to n-1, you get the structure of degree +1, which is precisely what you want to have. And if you apply this to certain AKZ theory, then the theory that produces Chern-Simons theory will be a theory in 4 dimensions, you get precisely the example we had before. Not every theory is an AKZ theory. In particular, AKZ theory are topological. So, we want to do gravity. Gravity is invariant under diffeomorphism, but it's not topological because it has some local degrees of freedom. So it turns out it's not AKZ, but still you can go down to the corners by a different procedure and see what happens. And it turns out that the end is essentially the same as 4-dimensional BF theory plus these additional constraints. And okay, I think I can stop here.
So thank you. So any questions? Questions?
So you mentioned corners in 4D BF theory.
Yeah.
There's people like Davide Gaiotto and collaborators study certain chiral corners in 4-dimensional or twists of 4-dimensional supersymmetric theories.
Yes.
That support vertex algebras.
Yes.
Do you think those vertex algebras should be, in some sense, quantizations of the P infinity structures?
But they start from the chiral theory, right? So it's a different theory.
I mean,
but it's probably the same.
With like a topological twist of a 4D theory. They just study boundary conditions that are not.
Okay, so but say that basically they start from the theory, essentially.
Yeah, more.
Okay. Oh, okay. So we look. Yeah. Okay. Yeah. That could be. Yeah. Sorry. Thanks.
Further questions? Actually, I have a question. So if you come back to one of the examples that you considered initially, so when you have Lie algebra functions, Lie algebra valued functions on M2, so you introduce a cos cycle, and then you added another term with which cosmological
Yeah.
constant. So I just wonder. So we know for affine case, for affine algebra, so that this we have one-dimensional space of homology, and here is two-dimensional.
It seems to be two-dimensional. Yes.
Yeah.
Yes.
Is it
Maybe more? I don't know. Maybe more. Yeah. This is what we found. Yeah.
Okay. Right.
So, but yeah.
Okay. So you can multiply one first cycle by something, and the second by cosmological constant, and altogether you have two-dimensional, at least two-dimensional. Just center extension governed by two parameters.
Yes.
Yeah. Okay. Thank you. So any further questions? No questions on chat?
No questions in the chat.
Okay, let's thank the speaker again.